Hello students, as uh, the task of addressing the control hazards was being looked at, we started with a discussion on can we do something at the fetch stage, and accordingly we said uh, we have something called branch prediction, and for that we need to answer three questions. First is whether we can identify that the instruction we are fetching is a branch or not. The second question is if we know it's a branch, can we make some guess whether it will be taken or not taken? That is the branch prediction part. And the third question is if it is taken, where will it go to? Meaning the target address. So in the last class, we looked at the first and third questions and said we would need a hardware called branch target buffer, which you can imagine as an array of addresses, and the addresses that it stores is of the control instructions, and it will also store the target address of that branch when it is taken, right? So uh, PC or the address of the instruction itself is used to index into this BTB. And for the sample program that we studied, the entries were something like this. There was a branch instruction in line number 14, which if it were taken would have uh, gone to line 29. Another BEQ was there uh, in line 22. If it was taken, it would have the control would have reached L25. And there was a JL instruction in line 24, which always will be taken, and it would the control would reach to L26. The same thing would happen for the JL instruction in L28. It is always taken and it would go to L14, right? We replace them with the actual addresses, which is 0x24 is the address of the first BEQ instruction and its target is 0x60. 0x44 was the address of the second branch instruction and its target was 0x50. 0x4c was the address of JL and it would go to 0x54, and 0x5c was the address of fourth branch control instruction, which is again JL, and it would go to 0x24. This was for the sample program we took. So when we start executing a program, the BTB is all empty, and as and when we execute a branch instruction, the BTB gets populated with its the instructions PC and the target. The next time the same instruction is fetched, we use the PC and check the BTB if there is an entry or not. If there is an entry, then we would take the target address from there. And if there is a hit in the BTB, meaning that there was a PC match, then we'll definitely know that the instruction we are fetching is a control instruction. That's when the second task, which was the actual prediction of that control instructions outcome, will take place. So the design challenges were mentioned, which was to decide on how long the branch target buffer can be. If it is too short, what might be the possible issues, because we might not be able to fit all the branches in the BTB, right? So BTB sometimes is also referred as branch target address cache, right? The word cache might be totally new to you, but for now just go with it. I'll explain it in the memory module. Moving on, the main important question for the branch prediction is how do we actually predict the outcome of a control instruction at the fetch stage itself. So using the PC and the target, we are able to find out that it is a control instruction, and if it is taken, where will it go to? But how will we determine whether it will be taken or not taken? Because this is a prediction. We are not actually resolving the branch. In fact, we are not even looking at what the branch is, right? We don't know, make a note that it, the control instruction that we are bringing in is a BEQ or BNE. We just make a note that it is a control instruction. We are not going to store any other information in this regard. And another note is for jumps. The moment we know that it was a jump, the very first time it got executed, in the decode stage we will know whether it is a jump or branch. For jumps, we know that they are always taken, so we don't need branch prediction for this, right? We can always say it would be predicted taken. So these two are important points that we need to know for branch prediction. We are going to predict only the branches, not the jumps, and we are not going to resolve the branch, but basically predict its outcome, whether it will be taken or not taken. Now, if somehow we are making a prediction and we have built some hardware for that, how do we know that the hardware is good? How do we measure the effectiveness of such a prediction? Right? So for that, we have very specific metric which is called prediction accuracy. Let's say we have predicted some 100 branches, right? For each of those 100 branches, we would have predicted taken or not taken, etc. Right? And in the fetch stage, when the particular branch got executed, we will know the exact outcome, whether it was actually taken or not taken. Right? Now our prediction, let's say, is taken and the actual outcome is not taken, then whatever we predicted in the fetch stage is actually wrong. So those events are called mispredictions, right? The actual prediction of the branch that we will know when we executed it is not same as our prediction at the fetch stage. That is a misprediction. In case they are same, let's say we have predicted for some particular branch it will not be taken, and when we executed the branch it was indeed not taken, then it is a prediction hit. So the prediction accuracy now is number of prediction hits or correct predictions upon the total number of predictions we made. If you take an example, say for some particular program we have made predictions for 100 branches, right? 100 times basically, and of those 100 times, 60 times we made correct prediction. It means that whatever we predicted matched with the actual branch outcome. In that case, the prediction accuracy of our branch predictor is 60 upon 100, so it is 60%. Okay. Now, whenever we are proposing or analyzing a branch prediction mechanism, we look at the prediction accuracy and we try to understand whether it is good or bad. Okay, keep this prediction accuracy in mind from now on, as long as we are discussing the branch prediction. This will help us to appreciate the branch prediction's effectiveness. Now the important question, how do we predict the branch outcome? Primarily, there are two different approaches, right? There are static branch prediction and dynamic branch prediction. As the name says, static branch prediction is kind of fixed for the lifetime of the program. But dynamic branch prediction tries to adapt itself to the changes in the program behavior. Static branch prediction, the biggest positive is it's quite easy to implement. On the other hand, dynamic branch prediction needs complex hardware to implement. Static branch prediction's accuracy is quite low because it is not adapting to the program, right? It is not learning. Basically, it just says this is my prediction and I'll stick to it all through. So the accuracy is quite low. And when it comes to the dynamic branch prediction, its accuracy is usually higher than the static branch prediction. The exact accuracy of the dynamic branch prediction is determined by what predictor we have implemented. We are going to look at quite a few predictors. From there, we can make some comment on their accuracy. Okay. Before that, let's start with the static branch prediction. Like I said, it remains constant or same throughout the execution of the program. So one of the simplest prediction we can make is whenever we know that the instruction we have fetched is a branch, we will say always predict it will not be taken. It means that the very next instruction we are going to fetch is the next sequential instruction, right? Now, when is such a prediction most effective? It was found that usually the branches which are forward, means where we are jumping to some place later of this instruction, control instruction, they are usually not taken. But this is an observation that was made, and the implementation of always not taken is quite simple, right? And we don't need even the branch target buffer too, because there is no notion of target here. Target would only come when we want to predict that it will be taken. And when it was tested out on the real hardware with the actual programs, its accuracy was found to be very low. This was implemented in Intel i486 processor in 1997. And the other end of the static branch prediction is I will predict always the branch will be taken. So this is exactly opposite of the first technique, right? And when is it typically effective is for backward branches. That is a popular example is loops. Whenever we loop, we are going back to few instructions before, right? So it is a backward branch. So, and if there is a loop, let's say iterating 100 times, right? So for 100 times, when we say that the last branch will be taken, it means that 100 times we have predicted it will be taken. The 101 time it will not be taken. So the accuracy is 100 upon 101. And the implementation of always predict taken needs the help of BTB also, because we need to keep a store of all the target addresses. And when compared to the always predict not taken mechanism, always predict taken was slightly better. So the accuracy improved from 40 to nearly 70. Now, when we said that the most common observation was forward branches are not taken and backward branches are taken, can we use both of them together? That was what the backward taken, forward not taken BTFNT predictor was about. For forward branches, right, we will predict that it will not be taken, and for backward branches we'll predict it will be taken. Now the question is, how will we know whether the branch is a forward branch or backward branch? We already know the answer, because the immediate field of a branch instruction stores the offset. This offset is added to the PC, and that's when we will know the target address. Now, if the offset is negative, what it means is we want to jump to instructions which is before this control instruction. If the offset is positive, it means that we are going to jump some location which is later. So we know that if the offset is positive, it's a forward branch, and for such branches we are going to predict that they should not be taken, they will not be taken. And if the offset is negative, then we would say that it's a backward branch, and accordingly we will predict them to be taken. So BTFNT was quite effective, and it was implemented in Intel Pentium 4 processor, which came out in 2003. But as such, the static branch prediction was with limited capability, and over the years the nature of the programs has changed a lot. Because of that, static branch prediction has very limited implementation in the current processes, right? Another way of static branch prediction that was explored was using profiling. What profiling basically means is, before you actually run the program, you are going to run it once with some sample data, or you can say the test cases, right? And the compiler will now study the nature of each of the branches during the profile runs and make a note on how each branch is behaving, whether it is taken most of the time or not taken most of the time, etc. And once it makes note of this, it's going to communicate it to the hardware as hint bits if the instruction set architecture has some provision for it. For RISC-V, if you observe, all the bits of the control instructions are used up, right? So there is no provision to give hint bits, but some of the CISC type ISA have provision to leave hint bits, right? The compiler during the profile runs will understand what the nature of some particular branch is, and accordingly it will leave the hint bits. And at the hardware, we look at the hint bits. Let's say if it is 0, for example, then what the compiler is trying to say is this particular branch will not be taken. So accordingly, we will predict for that branch that it will not be taken. Now, on the flip side, if the compiler stores 1 as a hint bit, then we would predict at the hardware that it will always be taken. This is how the profiling based static branch prediction would work. Now, why such an approach would actually work is, what the designers or the hardware architects found was, typically a branch is highly biased either towards taken or not taken, and this would be we would be able to capture in the profile runs. And they also said that the profile runs are very giving us very good indication of the program itself, of the actual program. So based on this, they propose the profiling based static branch prediction, but unfortunately it's no longer relevant because of what I mentioned in the previous slide. Also, the nature of programs has changed. They are not so predictable now. The positives of profile based static branch prediction is its accuracy was found to be better than the simple always taken, always not taken, or the BTFNT branch predictors, right? But on the flip side, it was found that uh, the demand from the profiling based branch prediction is that there should be some provision in the instruction format where it can, or the compiler can, leave hint bits. That is not usually case for all the ISA. And also the accuracy of the hint bits will be highly dependent on the profile runs that the compiler does. And the behavior of the actual branch will determine how uh, the hint bits, how useful they are. Let's say the hint bit was saying 0, but always the actual branch outcome in the actual run was taken. So the hint bit was useless in that case, right? So the static branch prediction, in summary, will not be adapting or learning at the runtime. Because of that, the static branch prediction mechanisms were uh, discarded, and more sophisticated dynamic branch prediction mechanisms were proposed. Now, if you are wondering why all this headache for just control hazards, if you remember, the first lecture in the control hazard was looking at the branch penalty, right? If we had not moved uh, the branch resolving hardware, like the comparator, from the execute stage to the decode stage, we would have uh, paid 2 cycles penalty. But we saved 1 cycle and tried to do the branch resolution in the decode stage itself. Now, if the prediction is correct, then we will even save that 1 cycle, right? And let's say our program has 1,000 branches, and if we don't use branch prediction or anything, these 1,000 branches will result in 1,000 stalls or 1,000 flushes in the pipeline. Means 1,000 cycles are wasted just like that. But if we employ some prediction and let's say its accuracy is 60%, it means that out of these 1,000, 600 branches were predicted correctly. It means that we have saved 600 cycles. The additional drop in the performance because of the control hazards earlier was 1,000 cycles, now it is only 400 cycles, right? That is the reason branch prediction was taken up very seriously, and lot of interesting works were proposed, but not in static branch prediction, in the dynamic branch prediction. That's what we are going to study in the next couple of classes. With that, I will pause now. Thank you.